In this video, we take a deep dive into the world of high-tech materials driving the next generation of Internet of Things devices. From flexible sensors to bio-integrated electronics, materials science is unlocking new form factors, capabilities, and levels of performance in IoT. If you enjoy insights into advanced materials and their real-world impact, please like this video and subscribe to our channel for more technology deep dives. 1. Why materials matter in IoT. Every IoT device relies on more than just microchips and antennas. Materials define size, flexibility, power consumption, durability, and cost. Conventional silicon and FR4 PCBs have dominated electronics for decades. A shift in materials can transform IoT from rigid boxes to integrated fabrics and bio-friendly interfaces. 2. Graphene. The wonder material graphene is a single layer of carbon atoms in a hexagonal lattice. In 2025, we see commercial wearables using printed graphene biosensors for sweat analysis and hydration monitoring. 3. MXenes and 2D materials. Beyond graphene, MXenes offer a new family of 2D materials composed of transition metal carbides or nitrides. In photodetector applications, 2D semiconductors enable on-chip light sensing for environmental or optical communication functions. 4. Conductive polymers and hydrogels. Conductive polymers, like PEDOT, PSS, and conductive hydrogels bridge electronics and soft materials. They are key for stretchable sensors, bioelectrodes, and patch-like devices. 5. Nanocomposites and functional coatings. Nanocomposites combine carbon nanotubes, metallic nanoparticles, or silica into polymer matrices. They can be tuned for conductivity, mechanical strength, thermal management, and sensing. 6. Flexible and stretchable electronics. Rigid electronics limit form factors and interface options. Advances in stretchable circuits, printed electronics, and soft interconnects enable circuitry that bends, folds, and stretches. Examples include e-textile health monitors, motion capture suits, and conformal vibration sensors for industrial equipment. 7. Bio-integrated and transient materials. For medical IoT, materials must be biocompatible or even transient. Biopolymers such as PLA, silk fibroin, and cellulose derivatives can be used to create devices that dissolve after use or safely reside in the body. By 2025, prototypes include biodegradable pressure sensors and implantable electrocardiogram devices. 8. Energy harvesting materials. IoT is often deployed in remote or battery-limited contexts. Energy harvesting materials are critical. Piezoelectric materials like PZT and PVDF films convert motion or vibration to electricity. 9. Photovoltaic and photodetector materials. Mini solar panels using thin film SIGs or perovskites are embedded into IoT devices. These panels provide continuous power outdoors for agriculture sensors, streetlights, and asset trackers. In safety systems, they detect fire or combustion via infrared emissivity changes. 10. Advanced dielectrics for capacitive sensors. Capacitive touch and proximity sensing are important in consumer IoT. High-K dielectrics like hafnia or barium titanate enhance sensitivity and reduce size. 11. ME shielding and electromagnetic compatibility. Dense IoT networks and 5G-enabled modules require strong ME shielding. Materials such as MXene films, metal particle composites, and conductive elastomers provide thin, flexible shielding layers. 12. Thermal management materials. High-performance edge computing modules and AI sensors generate heat. Thermal interface materials, graphene aerogels, and phase change composites dissipate heat passively. 13. Mechanical durability and self-healing materials. IoT devices deployed in harsh environments need to survive drops, impacts, chemicals, and wear. These materials extend device lifespans and reduce maintenance costs. 14. Transparency, aesthetics, and form factors. For consumer IoT, smart mirrors, transparent displays, home hubs, materials must blend functionality with design. Transparent conductive oxides, silver nanowires, and graphene films allow electronic layers to disappear visually. 15. Sustainability and recyclability. As IoT deployment scales to billions, sustainability becomes essential. Materials designed for ease of recycling, biodegradability, and minimal environmental impact are gaining attention. 16. Eco-friendly conductive inks. Printed circuits are realized through inks containing silver, carbon, or copper nanoparticles. Low-temperature sintering carbon-based inks enable printing on biodegradable substrates. 17. Emerging multifunctional materials. Researchers are experimenting with materials that combine multiple functions: strain sensing, thermal regulation, solar harvesting, and ME shielding in one layer. 18. Challenges in materials integration. New materials often require specialized fabrication: CVD for graphene, sputtering for MXene films, cleanroom for 2D materials. Scaling to mass production remains a hurdle. 19. Standardization and industry collaboration. Standards bodies and consortia are working to certify materials and processes. Interoperability specifications are emerging for flexible electronics compatible with major platforms. If this video sparked your interest in the science behind next-gen IoT, please like the video and subscribe to our channel. Turn on notifications so you are always the first to hear about our latest content in emerging technology. Leave your thoughts and questions in the comments. Thank you for watching, and we look forward to seeing you in the next exploration of tomorrow's tech.